Let me get started first by introducing the topic that I would like to talk about today. So, we have, I think, all heard about sustainable development and sustainability in the built environment, reducing the impacts of the building sector, because I believe most of us have some experience with the building sector or green buildings or sustainability and so on. However, I'm going to try to introduce a concept which you may have already heard about, life cycle thinking, and how it relates to the sustainability initiatives in the built environment. Now, moving on, we will discuss about the sustainability in the built environment and the sustainability interventions that we use to reduce the impacts and improve the environmental performance and maybe economic and social aspects related to the built environment, and the costs and benefits of engaging in these interventions. And based on that, the need for life cycle thinking. Why do we need to apply life cycle thinking in the sustainability initiatives? And with that, I'll introduce the concept of life cycle sustainability assessment, building sector applications of life cycle assessment, and we'll go over some case study examples of some analysis we have done using life cycle assessment in various industrial applications. Before moving on to the core topic, I would like to ask this question from you. What is sustainability? This is a word that is almost overused. You hear it everywhere. Sustainability, sustainable development goals. So there's a big hype about sustainability and also a concern that we are overusing this word, that this word is now getting outdated. So today you hear more about sustainable and resilient development rather than taking sustainability by itself. So the core concept of sustainability or sustainable development is whether we can meet the needs of the present generation, those who live today, without compromising the ability of future generations to meet their own needs, without borrowing from the future. So we try to, if we are going for sustainable development, we try to maintain or improve the standards of living today without damaging or depleting natural resources available for the present and future generations. In doing this, we look at three main dimensions: people and their quality of life, fulfilling the needs of people, while ensuring societal progress and preserving the environment. So essentially, you see these three dimensions: people, progress, and environment. Now, in integrating sustainability into the built environment, we first need to look at what built environment means. So the term built environment essentially refers to all man-made infrastructure. The buildings we live in, the distribution systems, the water distribution systems, the energy systems, the waste collection systems, all these systems that enable us to maintain life as it is, that enable us to have the human civilization function. So water, electricity, roads, bridges, transportation network, all of this, it is a part of the built environment, things that people have made, when humans have made in order so that they can have a sufficient quality of life. So we spend most of our time within the built environment, and the built environment accounts for 10%, around 10% of the global GDP, and about 1/3 of the global final energy use. And it generates around 40% of the global energy related emissions and consumes almost half the global raw materials. So a key challenge that we have today is to integrate sustainability into the built environment while also fulfilling our needs. So why do we consume all these resources and why do we consume all this energy? It is to fulfill our needs. The need, it can be to live, to engage in industrial activities, to for leisure or entertainment activities, to ensure our own comfort. So we have various needs to fulfill within this built environment. So the challenge is, how do we integrate sustainability while also making sure that we are not adversely damaging the environment and the quality of life of the future generations? So when we do this, we look at this concept called triple bottom line sustainability. So when we hear the term sustainability, what first comes to our mind is environment, in an environmental preservation. However, sustainability is not just about the environment. It is also about the economy and the society. So true sustainability means that we are being environmentally responsible while maintaining economic viability and social responsibility. So we try to maintain and improve the quality of life for people while contributing to economic development and reducing the environmental impacts. So we call this the triple bottom line in engineering decision making, or for that matter, any sort of decision making. So sustainability is built upon these three pillars. In order to achieve this sustainability, planning is essential. Planning and proper decision making. And we apply this thinking in developing energy systems or designing products, or in planning and implementing urban infrastructure, or developing industrial systems. No matter what it is, we have to think of the triple bottom line of sustainability. Now, these sustainability interventions, things that we commonly do in order to reduce the environmental impacts and improve the environmental, economic, and social benefits. These are some common sustainability interventions when it comes to the built environment. Reducing energy demand, and then reducing the water use, especially fresh water use, trying to recycle the gray and maybe even black water in buildings, so that instead of using fresh water, we can use recycled or reclaimed water. And then reducing the amount of waste generation and then recycling, using renewable energy, and then mitigating emissions through technologies like carbon capturing and utilization. So in buildings, you can actually, even at building level, so this is commonly used at power plant level, but even at building level, you can capture the carbon emissions in the flue gas by retrofitting it with carbon capturing technologies. And then using low impact, maybe recycled and non-toxic materials for construction. And then shared mobility, like ride sharing, and low impact mobility, like moving from, let's say, motorized transportation to walking or cycling. So many cities across the world, now they try to go for, let's say, these low impact mobility modes by replacing the conventional transportation pathways with cycling and walking paths, and then improving the occupant well-being through air quality improvements or thermal comfort enhancement, or let's say passive lighting and ventilation strategies. So all of these are sustainability interventions that we could use in the building sector. Now, when it comes to the building sector, energy use is of special importance because this is responsible for most of the impacts in the building sector. So it accounts for about 30 to 40% of the global energy consumption, the building sector. And because of this, you see, many households are affected by energy poverty. If you take Sri Lanka, for example, now Sri Lanka is a hot country. And with the recent changes in the environment, especially the extreme climate events, you see that many people are suffering from heat stress in households as well as in, let's say, commercial or institutional facilities, for example, schools. Because energy is so costly and people cannot afford active air conditioning, vulnerable populations, especially aged people or children or sick people, they suffer from heat stresses. Similarly, you see the other side of the coin when you go to colder climates. So they have to spend a whole lot of money on space heating the built environment that they live in. So significant portion of their paycheck goes towards energy bills. So if a household has to spend around more than 10% of their income on procuring energy services, we say that they are affected by energy poverty. So many households across the world, they are suffering from energy poverty. And we all know that there are environmental impacts of energy use, adverse environmental impacts. The most apparent one or the most talked about one being greenhouse gas emissions contributing to climate change. So because of that, there are climate action initiatives across the world. And with energy use, we see all these problems. The demand is increasing across the world, especially with the increasing industrialization. There are environmental concerns. The supplies are constrained, and there can be issues like the current ongoing Russia-Ukraine war that introduce further constraints in getting the supplies to the consumers. And the economic burdens with the increasing demand and the increasing energy prices, it places a huge economic burden on the people and industrial entities. So because of this, sustainable community planning or sustainable development, introducing sustainability to the building sector is essential. So there are two main ways we go about doing this: demand reduction and then replacing the conventional energy supply with on-site renewable energy. Renewable energy, but preferably on-site generated renewable energy. So we call these clean energy initiatives for buildings. And we use these initiatives to develop near zero or net zero buildings. And I will go into the net zero concept in a bit, but what we try to do is essentially to reduce the demand and supply the remaining demand with renewable energy or clean energy as much as possible. So there are good things about these green developments. Green rated buildings or green rated products can fetch up to price point increase of up to around 9%. However, there are also barriers and challenges in doing this. One thing is the conflict in objectives. Now, we previously discussed that we want to derive economic benefits, let's say energy cost savings or reduced investment costs, while also making sure that the environment is preserved and people have a good quality of life or the society is benefiting. So these things conflict. Usually these green technologies, if you want to integrate a green technology into a building, you have to incur an additional cost. So here the environmental and the economic requirements are conflicting with each other. And then it may be that if you want to, let's say, integrate renewables or retrofit a building, there are high investment costs. And the investors or the building owners sometimes are not very sure or they are not certain about the benefits of doing something. And perhaps, let's say, even if they do want to go about doing this, there's a lack of expertise. An average building owner would not necessarily have an idea about what the best solution is to his or her building or what they should invest in with the limited funds that they have. So these are some barriers that, let's say, that challenge or that prohibit the increased penetration of these sustainability initiatives in the building sector. Now, like we discussed, so we can go for demand side management or we can replace the supply with renewables. So what is demand side management? We try to reduce or modify the consumer demand for energy through different technological, educational, and policy measures. So these can be applied in the residential sector or commercial, agricultural, industrial or transportation sectors. But what we essentially try to do is we try to reduce energy costs, energy use, and the associated energy costs by various technical, educational, or policy measures. We may try to also move the energy use to off-peak hours rather now by using, let's say, time of use tariffs. We try to discourage energy use in peak hours. Why do we do this? Now, if you have more and more peak energy demand added, that means in order to supply that demand, you have to install new capacity in the generation infrastructure. You have to add new capacity, new power plants to the power generation infrastructure. So this is essentially, if you can actually defer some of this demand, you can save on that infrastructure development cost. You can, let's say, prevent waste. So in order to do this, we try to shave off the peak. In addition to that, we also try to mitigate emissions and other negative environmental impacts by introducing demand-side management measures. Now, so what are some of the key demand-side management measures that you see in the building sector? One thing is energy efficiency, and the other one is demand response. Energy efficiency is essentially about reducing the amount of energy that we use in performing some tasks, reducing the amount of energy. And then demand response is about shifting the demand away from the peak hours or trying to flatten the demand. So by doing energy efficiency interventions, we try to reduce the energy costs by reducing the amount of energy used in doing something. For example, in heating water or cooling the space that we live in, we try to improve the efficiency and reduce the demand. We can try to minimize the passive solar gains, thereby minimizing the indoor heat gains. Or we can try to recover waste heat and use it in some process heating or water heating applications. By initiatives like this, we are trying to essentially reduce the amount of energy used. So it can eliminate energy poverty, mitigate emissions and other environmental impacts, and also reduce the reliance on imported fossil fuels. Other benefits of both energy efficiency and demand response is that we can reduce the strain and the costs on the power system, the need for additional power infrastructure, the strain on the existing generation, transmission and distribution infrastructure, and avoid new capacity additions, and increase grid reliability. So all of these benefits can be achieved by simply investing or simply taking an effort to do demand-side management initiatives. Now, energy efficiency can be achieved by technical or design means, and demand response can be introduced through policy or behavioral interventions. So here you see some of the specific interventions. Now, energy efficiency through it, the energy efficiency aspect, it can be further classified as efficiency, savings, and conservation. So by efficiency, we mean that we are maximizing the useful energy output of, let's say, an appliance, a washing machine, or an electric light, or a refrigerator, by minimizing the waste. Therefore, we are reducing the required energy input at appliance and system level. So how do we do this? By introducing new technologies or replacing older and less energy efficient equipment, using automatic controllers or energy rating for equipment, and energy savings where we replace active energy consumption through passive means. For example, by the use of natural lighting or passive ventilation to reduce the need for active lighting or air conditioning. We can do this by orienting and having the building shape in an optimal manner, using materials that reduce heat transfer and avoiding thermal bridges, using better insulation and window or basically fenestration designs, and using natural lighting and ventilation. And then conservation, using conservation practices to inform people about their energy use and to reduce unwanted energy use using smart energy meters or automatic switches or automatic controls to turn on and off the appliances and lighting, and education and awareness, and using pricing, time of use pricing, discouraging energy use at certain times of the day, and so on. So these are all different types of energy efficiency interventions. Demand response, again, can be via technological interventions and by changing the consumer behavior. So we try to schedule the appliance use to certain times of the day by maybe technological means, by turning them on and off at different times of the day, or smart grid applications using intelligent energy storage. And we can also change consumer behavior through awareness programs or providing incentives to change their energy use, financial incentives or other incentives to change their energy use patterns, or using time of use tariffs or peak pricing, and by using smart home displays that allows people to see how they are consuming energy and where energy is getting wasted. And smart metering with price variations and direct load controls. These are all demand response interventions. So with all of these, we are trying to go towards a low impact building sector. We have various concepts when it comes to a low impact building sector, green buildings, and then net zero buildings, or code compliant buildings. So green buildings are buildings that essentially reduce or eliminate the negative impacts through design, construction, or operation. Net zero buildings, the concept that I spoke of earlier, is where we try to reduce the energy demand and we try to supply the remaining reduced demand through on-site renewable energy. And we have now building codes that standardize the construction of buildings. So that buildings have to be constructed to meet specific standards for higher energy efficiency. Or even the existing buildings we can retrofit for improved energy efficiency by upgrading the energy consuming systems, perhaps the 3AC system or the envelope components through maintenance, replacement, and additions. Passive buildings, now they take this a step beyond. We develop ultra low energy buildings or buildings with extremely reduced energy consumption through passive energy saving means. So these are all things that we can do in order to reduce the impacts of the built environment. The other concept is using renewable energy. This can be done at centralized level, as we have all seen, with centralized renewable energy generation plants, solar power plants, wind power plants, so, or at building level using passive and active technologies like passive solar heating, or active technologies like solar PV, solar thermal, or geothermal heat pumps, ground source heat pumps that allow using the static temperature in the ground to heat or cool the space as required. And then biomass systems and wind turbines at building level. So electricity, heating, and cooling end users we can fulfill through renewable energy technologies. And we can integrate these into both new and existing buildings and thereby reduce the energy related impacts. Now, these are all sustainability initiatives. So far, so good. So we all know that it is sustainability is a good thing. This is common knowledge or common belief. So why do we need life cycle thinking? Life cycle thinking is where we try to obtain a more holistic impact, a holistic vision about the impacts of any project, process, or decision. Now, for example, we say integrating solar PV, solar energy at building level, leads to zero emissions. We know fossil fuel based energy, we have in generating for, energy from fossil fuels, we are combusting the fossil fuels. So it leads to emissions. Now, if you take a solar PV system on a rooftop, there are no emissions. So we call solar PV zero emission. But the thing is solar truly zero emission? The conventional measures of environmental impact assessment, they usually focus on a limited scope in time and space. For example, so this solar PV issue, we are looking at the operational phase. When the energy generation takes place, solar energy does not produce emissions. However, in order to extract the raw material to produce the panels and system components, to manufacture those components, to transport and assemble them, to install the system. And finally, when we are disposing of the panels and the components at the end of the life, there are going to be environmental impacts. To extract the raw material, we have to spend energy. To conduct the manufacturing process, again, we use resources and energy. So this energy may come from different sources depending on the grid mix. Because of that, it has embodied emissions, we call it. So embodied emissions are integrated into these panels because emissions, there was an active energy use, and therefore a release of emissions that took place in producing this system. And at the end of the life cycle, waste matter is generated. Solar panels, solar PV systems in particular, they contribute to electronic waste, and electronic waste is really difficult to dispose of without creating negative impact on the environment, without creating a damage. By applying life cycle thinking, what we try to do is to see these upstream and downstream impacts from resource extraction to eventual disposal without simply thinking about the operational phase. So when we apply life cycle thinking into engineering projects, it helps us to get a more holistic or a more complete picture to see whether, yes, we are hoping to obtain benefits, but are we truly obtaining benefits, or does it come at a higher cost than we intended? And it addresses not only the environmental aspect, but also the social and economic aspects. So the three pillars of sustainability. Now, why do we need life cycle thinking in enhancing the sustainability of the built environment? Now, sometimes we do things hoping for a positive outcome, but it can lead to another adverse effect down in the life cycle or later in the future, an unforeseen negative consequence. One example I have is based on a recent study that we conducted. Now, in cold climates, insulation is integrated into the building envelope so that we can reduce the thermal energy requirement, so that the heat is not lost. The heat within the building is not lost to the cold outside environment. So by using insulation, we can reduce the energy used for space heating. So far, so good. So we are reducing energy use and therefore the greenhouse gas emissions. But when we conducted a life cycle assessment on this, we found out that this leads to an increase in the ozone depletion impact category. So higher levels of ozone depletion or ozone damages, ozone depletion damage could be seen when we do this assessment. So when investigating the possible root cause for this, it was identified that this insulation matter, when it is disposed of or when it degrades, it releases emissions that are damaging to the ozone layer. like chlorofluorocarbons. So these are ozone depleting. So while we are trying to achieve an improvement on one side by reducing the greenhouse gas emissions, we are having this unintended negative consequence of higher levels of ozone depletion. So we need life cycle thinking in order to select the best sustainability interventions, and in order to avoid unintended negative consequences, to assess different types of environmental damages arising from an activity, and to integrate these three pillars of sustainability into decision making. Now, taking the solar PV example that I discussed earlier, like I mentioned, there are going to be raw material and energy inputs in every stage, from, let's say, material extraction, the production of PV modules and other components like inverters, cables, and wiring, during the installation, and at the end of the life cycle, you have the waste matter generated. So while the use of solar energy decreases the operational emissions, it can add embodied emissions and other environmental impacts. So here you can see the overall environmental impacts of solar energy. And I'm not saying solar energy is bad. I'm simply saying there's more than what we directly see. So there's land use to construct solar power plants, leading to deforestation and habitat loss for different species. There is water use during manufacturing, cleaning, and cooling of panels. And then the obvious impacts of resource extraction. As you can see, the amount of materials required for one solar PV plant: 70 tons of glass, 56 tons of steel, 47 tons of concrete, 19 tons of aluminum, 7 tons of silicon, 7 tons of copper, and 6 tons of plastic. And when the panels are disposed after use, we release hazardous materials into the environment. And we still haven't found a perfect way of, let's say, recycling these solar panels without any harm. So now there's a huge solar boom across the world. And in 30, 40 years, when these systems go out of use, we will see a huge environmental problem across the world and in Sri Lanka if we do not find a good strategy of recycling and disposing of this matter. And then the obvious life cycle emissions during manufacturing, construction, and demolition. So these are the life cycle impacts of solar energy. Now, life cycle sustainability assessment is a standardized technique that we use in assessing all these impacts under the three pillars. Life cycle assessment, or LCA, refers to the process of evaluating the environmental burdens. Life cycle costing is used to assess the economic impacts during material extraction, manufacturing, installation, operations and maintenance, and disposal. And then social life cycle assessment, where we assess the social and socio-economic outcomes of doing something. For example, when we install a biomass plant in a certain location, are we contributing to the local economic development? Do we provide new employment opportunities to the people? Things like that can be considered in the social life cycle assessment. So I won't go into detail on this slide. This is simply to say that there are ISO 14,000 standards that standardize life cycle assessment, the framework and principles, and then the environmental management and environmental declarations and claims, like environmental product declarations or third-party labeling and certification programs. There are ISO standards that standardize and guide all of these processes. So this is not an ad hoc procedure. This has a scientific and standardized basis behind it. So in life cycle assessment, the environmental impact assessment part of it, we take a holistic perspective from raw material extraction to final disposal, covering design, manufacture, distribution, and use, all of these phases. We look at the raw material, energy, and water use, and we look at the solid, liquid and gaseous waste and emissions into the environment. And with that, we look at not only the emissions, not only the greenhouse gas emissions, but we also look at resource use and resource depletion, ecosystem damage, and then the impact of land use, human health impacts due to particulate emissions, ionizing radiation, and so on. All of these impacts, different types of impacts, without limiting ourselves into one type of impact. So impacts, and when we say life cycle assessment, we try not to limit ourselves to what happens on site, but we look at scope 2 and scope 3 emissions, things that happen during raw material extraction or the production of fuel and electricity and facility construction, and also downstream in the supply chain, goods and transportation and distribution, operation of sales outlets, and the consumption operation by end users and disposal. So we try to look at all of these aspects, whether it is a product, some infrastructure, or a process. We try to look at the upstream and the downstream without limiting ourselves to the on-site situation. Similar to the example I discussed with solar PV. And in this process, we try to, in the life cycle assessment process, we have 4 main steps. Defining the goal and scope, depending on what you want to see from the study, whether it is for policy development purposes, or whether it is to compare 2 different design options, or whether it is to select between different sustainability strategies for your organization. Depending on the objective of the study, we select the scope of the study and the boundary that we consider within that study. And then we try to quantify all the material and energy inflows and the outflows, all the energy that is used in the different phases, all the material inputs or water inputs, and how much of it goes into each phase, how much waste matter is generated at each phase, and what types. For example, yes, greenhouse gas emissions, furans, dioxins, any liquid waste, and again, different categories of liquid waste, any solid waste. So we try to quantify all of it. Based on this quantification, this inventory, we analyze the impacts, the damages like climate change, habitat alteration, human health risk, ozone depletion, acidification, eutrophication, all these damages on the environment. And finally, we interpret and report all of this. So here you can see one example, again for the solar PV example. We can assess it from raw material extraction for the panels to the disposal of the system at the end of its useful life. This is what we call a cradle to grave assessment. Or we can take a cradle to gate assessment. We are taking only a part of this value chain. We perhaps from the raw material extraction to the transportation, to the installation site. So we only look at this based on our specific need. We only look at these phases. Or it can be gate to gate. We are only looking at certain parts of this process. Maybe a product, solar PV manufacturer wants to reduce their on-site impacts. Because of that, they look at the parts, production, and assembly processes within their facility. Or it can be gate to grave, from the use phase to the disposal. It may be that someone wants to assess the impacts of using solar PV energy and then disposing of these panels. Depending on the requirement, the system boundaries can be different. Now, I think I mentioned about the applications. So different applications of life cycle thinking. So life cycle thinking essentially can be used for product or infrastructure design and renovation to select between different product options for green rated products or green rated infrastructure designs. If you have, let's say, you can achieve the same lead points, the same amount of lead points in building design through different strategies. But which strategy makes best sense when you take a life cycle perspective? Which one derives can can lead to most benefits. So for that sort of decision making, you can use life cycle thinking, life cycle assessment, costing, and social life cycle assessment. And then for purchasing and supply chain decisions, to select between different suppliers depending on their environmental performance. To when you are purchasing materials, alternative materials, we say eco-friendly or green materials for construction, but which one is a better material? One example I have is, or whether a certain material, eco-friendly, so-called eco-friendly materials are truly eco-friendly. Now, one project I have experience in, the research group was trying to develop green concrete aggregates. So we know construction and demolition waste is a huge problem. So they were trying to develop or construct a recycled aggregate from the waste matter. And the goal of our study was to see whether this makes leads to actual environmental benefits, or the energy and the materials used in developing the aggregate, it creates higher impacts than what you avoid by recycling this construction and demolition waste. It can be used for green certification or eco-labeling and to market yourself, and for sustainability performance performance assessment and benchmarking, to identify improvement opportunities, to develop regulations and policies, and for innovations, for green innovations. And one type of assessment we do here is whole building life cycle assessment, where we look at a building from the raw material extraction to the disposal at the end of its life cycle, the entire building from the design and to demolition for a given service life, for example. And we use this type of life cycle assessment to investigate the impacts of different design materials and choices, to obtain green certificates and labels, and to compare the costs and benefits of refurbishment versus demolition and reconstruction, and to support building sector policy development, or to make marketing or supply chain decisions, and to develop low impact technologies. So here you can see, we consider the product stage, construction stage, the operational stage, and the end of life stage in the whole building life cycle assessment. All of these different stages, and building information modeling, or BIM, can really help in this type of complicated assessment, because it allows you to have a digital representation along with a detailed bill of quantities. Life cycle costing, again, I'm not going to explain this in detail because this is what we are mostly familiar with. But basically, this helps us to quantify the economic costs and benefits of a product, process, or a project. And environmental and social impacts can also lead to economic impacts in the long run. For example, pollution and poor air quality can lead to health impacts. This essentially creates an additional burden on the healthcare sector. And we all pay, as taxpayers, we all pay to treat these illnesses. Or waste and contamination, even though, let's say, the waste in 30 years, the waste arising from solar panels, it has to be dealt with, and maybe the government will have to spend on it. So environmental and social impacts also lead to monetary effects in the long run. In social life cycle assessment, we look at both positive and negative social outcomes that impact society and people. The positive impacts can be job creation or better quality of life, economic development, and better opportunities. And the negative impacts can be things like health impacts or loss of property, exploitation, and then cultural issues. So we have to weigh all these costs and benefits against each other in coming up with a decision. So the interest of time, I will only go over a couple of examples so that you can have a better idea about the practical uses of this type of thinking. So these are all based on some studies that we have conducted. One thing is in planning building energy retrofits. Now, like I mentioned, energy retrofits, we have to incorporate materials and components to improve the energy performance of building. So depending on the building type and the location, you can have different types of retrofits to improve energy performance. So do these make real environmental sense when we consider about the embodied impacts in the materials and the components and the cost that we spend on them? Does it lead to actual positive outcomes? This cost benefit comparison can be done using life cycle assessment. So this helps us to identify what retrofit types have the best performance, what should be promoted and incentivized. This was a study done in collaboration with the municipality and a utility company in British Columbia, Canada. So they promote certain types of retrofits by incentivizing them. So for that, life cycle thinking is helpful. Life cycle assessments were used for this study. Another study that was done in collaboration with the city of Vancouver was about replacing older buildings. Now we all know older buildings have poor energy performance because they have not been constructed to code, or because the buildings have degraded over time, deteriorated. So whether we entirely demolish and replace these buildings, or whether we retrofit them and try to improve the performance and keep using them, this is a decision that the city planners and developers have to take. So in order to make this decision, we have to consider about the life cycle impacts of replacing the components and the energy performance improvement that you can obtain through the renovation and replacement, and the possible energy performance improvement we can get from demolishing the entire building and replacing it with a new building, versus the embodied impacts of that replacement. So again, life cycle thinking can help in a situation like this. Another example, so it's a building level example, is carbon capturing and utilization. Now, I think I mentioned that we can use carbon capturing and utilization to capture the carbon dioxide emissions in flue gas or in the emissions of power plants. Again, the amount of the captured carbon dioxide, the efficiency of capturing, and the embodied impacts and the environmental impacts can depend on the type of technology used and the efficiency of the process and so on. So what sort of capturing technology makes best sense, whether carbon capturing is feasible for building level carbon capturing systems, and then whether what sort of technology adaptation makes best sense, and how decisions should be made for optimal greenhouse gas emissions reduction. So this is something that we again explored with some industry partners. So these are all, let's say, possible applications of using life cycle thinking in industry for this. Oh, I want to explain one more example here. So pardon me for the title here. This should be replacing Chinese coal with Canadian natural gas. So Canadian liquefied natural gas can be used to replace the coal use in Chinese textile, chemical, and district heating applications. So by doing this, we know natural gas has lower emissions compared to coal. So by doing this, we hope that we can generate emissions reductions that can be used in carbon trading between the two countries. So basically, both countries can environmentally and economically benefit by reducing the emissions and also achieving carbon credits, trading carbon credits. However, while coal replacement at the end-use level with natural gas can lead to emissions reductions, natural gas production itself and then transportation to China has its own embodied impacts, embodied and other impacts. So by comparing these impacts at different stages and the costs, it is necessary to compare all of these costs and benefits to see whether it leads to an actual environmental and economic benefit in the long run. So this is again a study that was done in collaboration with a utility company. So I will stop there. Thank you for listening to my rather long talk. And I would be very happy to answer any questions that you have. Thank you very much.
Dear all, if you have any questions, this floor is yours. Yes, Mr. Swaraj.
Yeah, thank you, Dr. Hirushie Karunathilake. Actually, it's a wonderful presentation. We actually got several information. So, a small question in the recycling of these solar panels. So, do the Green Building Council or any other institution take initiatives to do this, the recycling of these solar panels or reuse of these solar panels?
So
That's
I'm not sure what about the initiatives taken by Green Building Council in Sri Lanka in this regard, but I can tell you that across the world, several organizations are now, let's say, taking notice of this matter. I recently visited the Aalto University in Finland, where they're conducting large-scale research on uh, the best ways of reducing, let's say, recycling solar panels. And but this is still at, I would say, R&D level. So the I don't think in most jurisdictions it has been mandated to, let's say, recycle these panels, or government mandated process is being carried out. So depending on the jurisdiction, there will be some initiatives, let's say, collect these panels at the end of the lifetime, and there may be some ways of treating with it, but the main barrier is still technological. Still, we have not perfected the technology to, let's say, recycle panels and separate the different materials and components, and maybe reuse some components and get rid of the toxic or hazardous materials. So not I cannot really answer as to whether there are government recommended or approved methods for Sri Lanka. But I can tell you that across the world, some initiatives are being taken on this.
Thank you, Doctor. Then with that, let's say the LED bulbs and the earlier days, the CD compact disc, we noticed in several places, several CDs and the LED bulbs are everywhere in the market. So similarly, in future, we may see these solar panels and solar PV items in everywhere in our garbages and some in the forest everywhere. So as a initiative of green concepts in Sri Lanka, Green Building Council doing a lot of work. So I think we must take initiatives to not to make hazardous by this sustainable development. Thank you, Doctor.
Yes. And just to add to that, like this has become a huge problem in Africa. So many African countries have been using these second-hand solar panels coming from China. It was all good for a while, but now that these systems have reached the end of their life, you see a lot of pollution in waterways and other compartments of the environment with the toxic matter released from these panels. So that problem is there.
Thank you, Doctor. Thank you for your answer.
Thank you. And are there any life cycle databases for assessment in Sri Lanka? So there are life cycle databases that we use in any case, like standardized databases like EcoInvent. So far, the data that we have specifically characterized for Sri Lanka is limited, but I think several academic institutions and organizations are now actively engaged in developing the life cycle databases customized for Sri Lanka. But in the absence of that, even without those specific databases, it is not that we cannot do life cycle assessments for Sri Lanka. We use the most, let's say, relevant data. Like in most cases, the data sets for geographically close locations like India, they are reasonably applicable to Sri Lanka. So, and for example, the solar panels we use in Sri Lanka are of Chinese or maybe Canadian or European origin. So in that case, we can use those data sets to assess the upstream impacts of those components. So like that, you can do life cycle assessments for Sri Lanka, but still, yes, the limitation of life cycle databases remains to be a challenge within the country. And about the recording, I'm not very sure. I think the host can provide a better answer for that, whether the recording will be shared.
Yeah, ma'am, we will share.
Okay.
Are there any questions? Otherwise, we can wind up the session.
Yeah, please notify that the attendance sheet is attached in the chat box, or otherwise someone may not notice.
Okay, so now we wind up our session. So thank you very much, ma'am, for taking time your busy schedule to be the resource person to the Green Talk and sharing your valuable knowledge. Actually, it was indeed a very informative and interesting session. So thank you very much again, ma'am. And as well as thank you all for being a great audience today. And dear all, please give me a few minutes to inform you about our upcoming courses. This is regarding our associate professional training program. If you want to be a green accredited professional, this is the first step for that. Our associate professional training program registration is now open. So you can register before 15th of January. And also our advanced course intake 7 registration is open until 13th of January. This course is designed for the associate professional of the Green Building Council of Sri Lanka and lead APs and any other recognized green professionals. As well as if you want to know more information about our training programs, workshops and other events, so please contact us through these contact numbers and emails. And you can follow us via these social media platforms. Finally, thank you. Thank you again, ma'am and dear all. Thank you very much. Stay tuned for upcoming events. Thank you. Have a great day.